Welcome to configuring ScreenOS firewalls. This is the section on IPv6 basic features supported in ScreenOS. For this session, we're going to cover the basic concepts of IPv6, the configuration of those basic features on a ScreenOS device. We're going to see how you configure policies then to use in ScreenOS to use IPv6, and we're going to be able to verify that the IPv6 operations that we configure are actually happening on the device. So the first section of the three that this is organized in then is IPv6 Concepts, followed by the actual configuration, and then the verification. IPv6. This is defined by the Internet Engineering Task Force, and it is in RFC 2460. This is our next generation of IP addressing intended eventually to replace the current IPv4, and it solves a number of the issues that we currently have with IPv4, chief among them being address exhaustion. So what are the differences? In IPv4 we have 4 sections of 32-bit address space. And to address the running out of addresses in IPv4, IPv6 doubles that to 8 bytes, and it uses 16-bit address spaces. So we move from a 4-byte to a 16-bit. And we move from 32-bit to 128-bit. So what does that mean in terms of numbers? In IPv4 we had 4.2 million addresses available in the total address space. With IPv6 that moves to 3.4 times 10 to the 38. So 10 to the 38 is an enormous number. For perspective, we're talking 10 to the 11 is trillions, so we're 3 times the size of being in the, more than 3 times the size of being in the trillions. In IPv4, NAT was utilized in order to extend the number of devices that can connect beyond the 4 million, as we're all familiar with in configuring throughout this lesson. Private addressing, behind NAT was a way to avoid having to consume, public addresses for every device, computer, network, printer, device on our network. With IPv6, everybody gets an actual address. So the NAT of individual computers and devices for internet access is no longer necessary, because everybody will have a live IPv6 address, and there's no private space that is not routed on the internet. In IPv4, you could choose to use either DHCP or static management. IPv6 continues to support DHCP to manually manage your network, but the intention is to replace this with what they call stateless auto configuration. Here you assign subnets essentially to router devices, and they, through a series of protocol negotiations with the device, assign addresses to everybody currently connected to the router. In IPv4, IPsec, which we had those 3 lessons on previously, is an optional feature that can be utilized to secure traffic across the internet. In IPv6, IPsec is built into the protocol, so it is part and parcel of the connectivity that's available in the stack. Options are included in the base headers in IPv4, so your header can change based on the IP options that are in use. And in IPv6, options are removed from the primary header, and they're included in the extension headers instead. So as a result, an IPv6 header is very, very predictable in both the length and the exact location of everything that's in the header, which helps then to optimize processing. So let's take a look at the IPv6 header. These are the sections that are available that are in every header, and you'll notice the size of the section next to each one. The most important change here is that the header is now a fixed size. It's always 40 bytes in length. This provides for very simple and more efficient processing. You no longer have to, a networking device no longer has to read the header and find the beginning, figure out how long it is, and find the beginning of each section of it. They're going to be in predictable and exactly the same spot on every header. And so therefore everything that changes in the header, the options, is moved into a separate area called the extension header. So this allows standard packets that don't contain any options to be processed in the fastest possible way in hardware. These are the fields that are deprecated. They were in IPv4, but they're no longer in use in IPv6. Obviously, header length first on the list there, because the length of the header is always the same. So taking a look at these side by side, our IPv4 versus IPv6 header. This is color coded then to show the items that have been removed in red, the items that are the same in that yellowish, and the items that have changed color in blue, and the one new field, the flow label there. So what you see is the size of the header is much bigger, because primarily because the source address and the destination address are much bigger. You know, they're twice the size per byte and twice the number of address sections, so that makes them much bigger. This slight renaming taking place in the blues. You know, we're changing type of service to traffic class. Time to live becomes a hop limit, which is essentially how time to live was being used anyway, as you know from IPv4. The total length of the packet becomes the payload length, since we always know the size of the header. And protocol becomes next header. So if there's things that have to change by protocol, they're handled then in in these supplementary fields instead of in the primary header. So what are extension headers that allow this to be done? They are packet headers. They are used for options in IPv6. So all of these option fields that were in the IPv4 header are now handled in the extension headers, so that special processing is not necessary on packets that don't require it. There are 6 defined currently in the standard, and these allow the control of the use of the options in the payload. So, whether or not you're encrypting, whether or not the packet's fragmented, authentication, and the like. These are all handled then in the extension header and removed from the primary header. Hop by hop options is letting you know that the option that needs to be examined at each node of a path in transit of a packet. So if there's a item that needs to be examined by every router, we put that in this option. The routing provides a list of the intermediate nodes that should be visited on the way to the packet destination. This can be used then for preferencing in path for routing. Fragment obviously lets us know that we've fragmented the data packet. Destination options are examined only by the final destination node, and they can appear twice in a packet. And then the authentication header and the encrypted security get used by the IPsec feature in IPv6. So taking a look at the address space, the address exhaustion on IPv4 is of course the major driver for this change occurring, since we now support this 3.4 times 10 to the 38 addresses. The address space goes from the millions to this multiple time trillion addresses. And at the current population, IPv6 has 2 to the 95 addresses per person on the planet. There are 3 IPv6 address types. Unicast is exactly the same as it is in IPv4, where we're having 2 nodes talking directly to each other. Multicast, again, exactly the same as IPv4, and defined and used in the same scenarios. The new one is this Anycast. Anycast is similar to multicast, only instead of everybody needing to get every communication as we do in a multicast environment, Anycast creates a group of resources where any of the resources can respond, but only one needs to take the communication, and then the rest drop out. So Anycast is a new method to find a IP resource that is closest to where the requester is. So you have a group of people that can provide a resource on the network. They're in an Anycast group. When you request that resource, the routing figures out which one of those Anycast addresses is closest to you, and then configures you to communicate with that address. So this is a step in between unicast and multicast, and a new feature in IPv6. Okay, let's take a look at the address notation and what addresses look like. This is a fully enumerated IPv6 address with all 8 sections and all 4 hexadecimal numbers in each section. So 8 16-bit addresses in hexadecimal separated by blocks of colons. There are some shortcuts we can use. We have some abbreviations to simplify this notation. For starters, if there's a leading 0, they can all be eliminated. So that brings that address down to this. You only need to put 1 0 instead of 4 zeros, and we drop the 0 before the 211. And so now we have a much shorter IPv6 address noted with dropping leading zeros. The next step in abbreviation is to use a double colon to indicate that everything between the 2 colons is zeros. So in this case we have 3 zeros in a row, so we drop all the zeros and just do a double colon. And now we can see in the bottom address we have 1, 2, 3, 4, 5 instead of 8 sections in our address. So that means we know there are 3 zeros missing. And you know where they belong. Now obviously if there's multiple sections with zeros, say BCFF and EF8C were also zeros, you cannot drop them too, because then you don't know how many are being dropped and where. So you can only drop the biggest section of consecutive zeros. So if our address were 2BFC 0, 0, 0, 211, 0, 0, 5B88, it would drop just those first 3, and we would have 2BFC double colon 211 0 colon 0 colon 5B88. So these are just ways to avoid having to write unnecessary or implied zeros in IPv6 addresses. There is a prefix notation in IPv6 that also uses a slash notation. This is defined in our RFC 4291. This is a similar shortcut to what we're familiar in IPv4 as CIDR notation. It does use the slash notation, and it's telling us the subnet that we are on and the size of that subnet. So it's including the beginning portion of the subnet and the size, just like CIDR does. So the prefix length, these are the reserved notations for special purpose devices. A unspecified address is double colons and slash 128. A loopback address is double colon 1 slash 128. And multicast is at FF00, and local link is at FE80. So those are the predefined addresses for those special purposes. Address allocation is pretty much the same as IPv4. You will get your IPv6 addresses from your ISP. The allocation methods are outlined in RFC 3177. And these are the scenarios. If you're a home user, they are to use a 48-bit prefix for home subscribers. If you're a small, medium-sized business or enterprise, they will also be assigning address space in 48-bit prefixes. If you're a large subscriber, they can go to 47-bit if you require that many addresses. And mobile networks are put on 64-bit prefixes. And finally, your single PC is going to be a 128-bit address that's part of a 64-bit allocation. So these are how the address space is being carved up and parceled out. These are rather large address spaces being assigned here. 48 bits is a lot of addresses. There are some special addresses reserved. A prefix of double zeros /16 cannot be used. The unspecified address vol zeros will not be used, and then loopback, when you're configuring loopbacks, is always going to be the :1 with basically all zeros and ones. So if you have an unroutable loopback address. Okay, let's talk about the new protocol that we have, Anycast, in IPv6. This is defined in RFC 2526, and this allows a packet to travel from one device into a group of devices that are providing something, and then only one of the group will handle and respond to the request. The routing protocols on the IPv6 routers then are going to be used to determine who is the closest interface in the Anycast group that should be responding to the request. Multicast in IPv6. This is a group of interfaces that are all belong to different nodes. They are all of the members of a multicast group are supposed to process the traffic as they receive it. And this is a way, just as in IPv4, to be more efficient than broadcast. So if you have a traffic that's needs to be delivered to multiple nodes and they all need to participate in the IP conversation, say a typical example would be an IP conference call scenario, or an IP conference call transfer, where you have, say, 3 IP phone endpoints that are all participating in the same conversation. They all have to get the packets to hear what's going on the call. So you don't want to broadcast that to everything on all those subnets, but you do need more than a one-to-one connection to be occurring. So in IPv6, these are designated by the FF start of the IPv6 address. And there are 3 types of multicast. The solicited node addresses are asking for the neighbor solicitation messages, the NS. All nodes are going to be multicast for router advertisement, and all routers are multicast addresses for people that are going to do router solicitation messages. So again, multicast conceptually and configuration wise is very, very similar in IPv6 as it is in IPv4. Okay, packet handling in IPv6. The most operating systems are able to do dual stack for their IP if they support IPv6. So essentially what you have is your network interface is going to be shared between the two protocol stacks, and your applications are going to be unaware of the underlying transport. They're going to be sending their application information, and the operating system involved is going to either encapsulate it IPv6 or IPv4 before sending it out to the interface. Now, you can use a couple of different methods to transit a zone. Say we have IPv6 traffic at location A. We have only IPv4 transit in intermediate areas, and then over at B we have IPv6 capable again. So there are two methods to transport our IPv6 across an IPv4 network. We can use encapsulation, where essentially the IPv6 packet and data are wrapped inside of an IPv4 packet, and then the router that understands dual stacks on both ends is encapsulating and de-encapsulating the information. The second method that we can use is address translation. You can do IPv6 to IPv4 NAT and reverse the process on the other side. So these are the two methods that allow IPv6 hosts or routers to communicate using IPv4 when the median between they have a native stack that's able to do it, but the median between doesn't support that. Okay, IPv4 compatible is the first type of method we have here for being backward compatible between IPv4 and IPv6. This particular technique is rarely used. It requires the use of a special IPv6 unicast address in order to carry the IPv4 information across the IPv6 network. You can use IPv4 mapped operation. This changes the IPv4 information transiting the IPv6 network by representing the addresses as IPv4 nodes only, as if they were an IPv6 address. So this technique addresses some of the limitations of the first one, and it allows the low order 32 bits of the IPv4 address to be directly used in IPv6. Okay, in the other direction we have 6-to-4 tunneling. 6-to-4 tunneling is a technique that allows IPv6 hosts, as we mentioned in the previous slide, to communicate over the IPv4 infrastructure by essentially encapsulating their information inside an IPv4 packet and then removing the encapsulation on the other side. There is a method called intra-site automatic tunnel address protocol, ISATAP. We love our acronyms. This technique is designed when you have a dual capable device separated by IPv4. The nodes then use an IPv4 address and create a special tunnel on IPv4 between the two. This is another tunneling type method, but different in structure than the previous one. And then we have Teredo addresses. Teredo addresses is another technique for connectivity between the IPv6 hosts if they're sitting behind a NAT device. And this uses UDP for tunneling the IPv6 packets that are part of the Teredo client's servers or relays. So this is another tunneling method. This is the third tunneling method to communicate IPv6 over IPv4. On the class website, each one of these methods has an RFC that defines exactly how it works. So they are all the RFCs for these are listed and linked on the site. For the most part, you don't really need to know how they work, but what you do need to know is that the two endpoints that you're trying to connect via whatever tunneling method you're going to use just need to be configured the same. Stateless auto configuration. This is how hosts in IPv6 get their address on PowerUp. Because stateless auto configuration is built into the host protocol of IPv6, it eliminates the necessity to have DHCP configured. Every host can be either statically addressed or statelessly auto configure themselves with the IPv6 capable routers wherever they come up. These are the elements that are necessary for stateless auto configuration. These define a set of communications back and forth between the clients and the routers that are on the subnets, and methodologically it is very similar to how DHCP works. So it creates a series of communications between the router controlling the IPv6 network and the clients. If there is no router controlling the subnet, there is a neighbor discovery protocol available, so that two clients that are IPv6 capable on the same network can establish communications with each other via IPv6 without the need of quote unquote the DHCP server, the router in this case. So stateless auto configuration allows a router to control this via these elements, or it allows two or more computers on the same subnet to negotiate this via neighbor discovery. Let's take a look at how this communications works. When hosts are powered up on the network and they have an IPv6 stack, they're going to generate their own link local address as part of the startup process. They will then do a broadcast looking for a RS, sending an RS message on the network, trying to find out if there is an IPv6 router that's controlling the segment. When that router receives the RS message, it then returns a prefix that it has been configured for this network, essentially telling the computers what subnet IPv6 wise this router is managing for the link they are coming in on. And then the hosts use that prefix in order to convert their link local address into the same prefix as been assigned by the router. So very, very similar to the process that we have now for DHCP. But the key thing here is that the process for generating this auto configuration doesn't have to be turned on like DHCP does on the the link level. It's part of what we do at startup here. Okay, the alternative to stateless auto configuration is a stateful auto configuration. This is defined in the RFC 3311 or 3315, and this allows full control then of the state using DHCP version 6. So if you don't want the routers to be selecting the prefix of the network based on what they know on the line, you want to control what addresses are deployed where in the network, you can use this. So you would use this when you need this full control over your IPv6 address space. You would use this when you want to have and control dynamic DNS assignments, and when you want to update DNS records from the hosts as they come up, and do automatic DNS updates via the DHCP methodologies. And you can also use this if you want to remove the MAC address components from IPv6 addresses. When these link local addresses are created for the hosts, part of what they're incorporating into the unique identifier is the MAC address to identify the host. So if for some reason you don't want the MAC address to be part of your IP addressing scheme, you can use DHCP to force the use of sequential or other addresses in the host bits. And it is important to remember that DHCP for IPv6 and IPv4 are independently configured. They're not the same DHCP server. They are independent units even on the same segment. Okay, IPv6 and NAT. NAT in IPv4 was really all about the address space limitations. When we started to hit address space limitations, NAT was developed in order to overcome the fact that we were slowly getting more computer devices than we had addresses. But what it did do is add a level of complexity to our operational and management infrastructure as a result. So the ideal scenario was to have an address per object, but with NAT address translation and port translation, we were able to share these addresses across multiple devices. So you can use NAT as a way to transition between the IPv6 and the IPv4 stack. This is really the only place NAT gets used in an IPv6 network. You're not going to be NATing IPv6 to IPv6. The address space and protocol is designed that everything's going to have its own unique address, and therefore it's not going to be necessary to do any NATing in the IPv6 world. But we can use NAT as with the transition method, to convert one address to another. In the ScreenOS devices, the DIP and the MIP are supported for this type of address translation. So when you need to convert cross stack, you can use the DIP or the MIP as the addressing method. Okay, so moving on, that's our background for IPv6, a very brief tour. Now we're going to look at where these configuration elements are in ScreenOS devices. There are a number of elements that go into setting up IPv6 on a ScreenOS firewall. first you have to enable the use of the protocol stack on the device. Then you have to choose whether the device is going to be in router mode or host mode for IPv6. Then you're going to choose the address and assignment methods. You're going to set up routing configurations based on IPv6 necessities. And then finally, you're going to have your policies. So these are the fundamental elements in using IPv6, and you'll notice that the last three are identical to what you need for IPv4. I mean, you have to assign addresses, you have to have routing for reachability, and then if you don't have policies, the traffic is denied. So the last three of these are exactly the same, just using the different address space. The first two are the only that are unique to IPv6. Host and router mode. In host mode, you are sending those RS messages we talked about before during the auto configuration process, and you're receiving the RA messages in order to auto configure on the network. In router mode, you're sitting and controlling the segment, and you're responding to the RS messages. So this is your first decision to be made in how the ScreenOS device is going to participate in the IPv6 network. Is it going to be the router that owns the segment that segment that it's attached to, or is it another IPv6 host that needs to be able to communicate in IPv6 on the network? So we're going to start off then by just turning on IPv6. This is only available in the CLI, and it's a multi-step process. By default, it's disabled. So when you do a get envar, envar, you can see here that the only thing returned initially is the default image of the ScreenOS. It does require a reboot after it is enabled. So when you set the second command there, set envar IPv6 equals yes, and then when we do the get again, you see that IPv6 is enabled. We of course need to save everything we do on the command line and then reset the device to activate the stack. So simple process, set IPv6, save, and reset. Okay, to configure IPv6 as a host on ScreenOS. Same process we're familiar with before. We're going to bind the interface that's the IPv6 interface to a zone. We're going to enable host mode on the interface and set an interface identifier. We're going to configure the unicast address. This is optional because it's a host. It can also use auto configuration, but if you want a static address, you would configure it. And you're going to configure your neighbor discovery so that it can fall back to finding other IPv6 hosts on the network if there's no response from a router to its requests for auto configuration. So that's it. 4 steps, and they're very similar to what we've already done in IPv4. Step 1, binding the interface to the zone. This is identical, so set interface Ethernet 00 zone untrust. Same exact commands that we used in the previous lessons, and the same location in the web UI. You're going to edit the interface and select the zone that the interface is going to belong to. Step 2, we're going to enable IPv6 host mode and identifier. In the configuration command line, these are all interface parameters. So set interface Ethernet 00 IPv6 mode host, enable IPv6, and then set our identifying address for the interface. In the CLI, this is also in the properties of edit the interface. There's a new IPv6 tab when IPv6 is enabled, and we're going to turn on IPv6 and enter the 64-bit unique identifier. So by default, you'll notice the unique identifier is the same as the MAC address for the interface. So these 64-bit ends of IPv6 addresses are generally going to be the MAC address assigned to the affected interface. And then, of course, in this case, we're saying we're going to be a host. Okay, step 3, configuring the unicast address. This is static addressing. It is optional. You can allow it to use auto configuration. But if you need to set a static address, it is still an interface parameter. So instead of the keyword IP, we're doing IPv6. Set interface Ethernet 00 IPv6 IP, and then the fully qualified IPv6 address. So here we're adding the static prefix FE80 to the beginning of our MAC address, because that's what we've assigned statically to this section of our network. In the interfaces, this is also in the IPv6 tab. You can assign up to 3 static addresses to an interface, and you just simply plug in the addresses exactly as you would an IPv4 address. Number 4, we're going to configure neighbor auto discovery. This is our fallback if we don't get responses from our router controlling the segment. So we're going to enable RA accept on the interface, and then this is the neighbor discovery section in the router advertisement incoming accept phase in the web interface. Also, again, interface parameters on the IPv6 tab. Then there's a sublink on the bottom, the end neighbor discovery /RA settings link. These are all the defaults for values. Okay, so that was host mode. If we're going to be a router and control the segment, these are the steps necessary. We're still going to need to bind the interface to the zone. We're still going to need to enable on the interface then router mode instead of host mode, and configure the interface identifier. Then the difference is a router needs to know the IPv6 prefix that it's going to pass out when it responds to these messages from the hosts on the segment. And then we're going to configure the address auto configuration. So the steps 3 and 4 are the unique parts of the configuration for router mode. Step 1, we're still setting a zone into an interface. So in this case, our Ethernet 00 being put into the untrust zone, which is also in the web interface under edit of the interface. Same place we were doing previously. Step 2 is also the same locations, but now we're changing keywords. So now we're going mode router instead of mode host. We're still enabling, we're still setting the interface ID, and then in the IPv6 tab, we're just changing the radio button from host to router. So step 2, exactly the same as the previous configuration, just changing the keyword from host to router. Okay, step 3. Static address configurations are again optional, and we can set our RA prefix. This is going to be the prefix provided by our IPv6 router to requests for auto configuration on hosts. So we set this as, in this case, 2BFB and the /64. This is in the prefix link tab. When you enable host mode, you get this new link called prefix list, and in here we're going to add a new prefix. Once a prefix has been added, they appear in the prefix list on the bottom of the interface. You can add multiple prefixes if that's required. So this will be the prefix that the router responds to auto configuration requests from hosts with. Okay, address auto configuration on the router. We're going to turn on RA transmit on the interface. This is again on that special link called the NDRA settings, and we set up the allow RA transmission checkbox in order for it to actually send out that prefix and allow it to respond to those RS requests. Okay, so that's how we configure our device to use IPv6 and be either a host or a router. Now we have to have reachability. We need IPv6 routes set up, so we're going to go over static routing. This is exactly the same as IPv4 static routing in terms of command structure. So on the CLI, we're going to use the set route command. The network we're going to route, the interface that it is reachable through, and the gateway we need to deliver it to. Exactly the same as IPv4, only we're plugging in IPv6 addresses. The web interface, exactly the same place. This is a new destination route in networking, and we fill out the IPv6 address and the IPv6 router that is going to receive it, and the interface that we can reach that router across. So these are exactly the same as what we covered in the previous section on routing. Policies. Now that we have reachability, we can control traffic by default again on ScreenOS. Cross-zone traffic is denied, so you must have a policy for IPv6 traffic to cross zones. Policy processing is identical to IPv4 policy processing. So you're going to create your IPv6 address objects as you need to control the traffic based on those addresses. You are permitted to mix IPv4 and IPv6 address objects in the same policy. So you can use either or both. And here you can see a sample of some policies configured using address objects in IPv6 and IPv4. You'll notice the special any object has been supplemented by enabling IPv6. We now have IPv4 any and IPv6 any objects available for use in our policies. And we can create address objects to IPv6 addresses. Now, this destination in policy ID number 4, 2BF2::64, this is, of course, can be any name. I mean, I've just used the IPv6 address as the name of the policy. That could say web server, that could say ISP, that could say data center. whatever the name of the address is. This is just for demonstration purposes here, that it's showing that that's an IPv6 address that is in that address object. So the creation process for addresses and the creation of policies, zone to zone, in this case, trust to untrust and untrust to trust. These are exactly the same as what we covered in the policy lessons. Okay, so now we've set up IPv6, we've configured the device, we've set up some routing and policies. We want to see if it's working. Troubleshooting IPv6 is going to use pretty much all the same tools that we've seen previously, and the same operations. So if you need to confirm that a configuration is in place, those configurations are on the interface, so you're going to be using your get interface command. If you're not able to reach something, you're going to use your get route varieties in order to see what's in the routing table. Ping and trace route are still available for your basic networking tools. If you're having policy issues or traffic being denied, our debug flow basic captures IPv6 traffic the same way it does IPv4. And with our policies, the get session is still in place. So all of these fundamental troubleshooting tools that we've reviewed in the previous sessions work exactly the same way for IPv6. Here's an output of the IPv6 configured interface. It shows the IPv6 configuration specifically for that, the neighbor discovery parameters, and how it's set up, so you can confirm that your configuration is in place. You can confirm that the RA on the interface is in place, and it shows the statistics that are associated with that interface for RA. All the information is at the top of the screen, and the prefix information is shown here at the bottom. Neighbor discovery is NDP is the keyword, so this is a new keyword entirely. This is get NDP is not from our previous lists, and it allows you to see if it's found any neighbors on the segment. So, wrapping up our IPv6 review here on the quick overview of the basic configurations. We've reviewed the concepts of IPv6 addressing and its notations. We've looked at the basic host router configuration of IPv6 on a ScreenOS device and how to set it up on the network. We've considered basic policy configuration and routing on IPv6. And we've looked at the commands that verify the operation of the IPv6 on the network. So this is what we covered in this session. If you have any questions about any of this material, feel free to post public questions or make comments about the material in the public forum on the class website. Or if you prefer, you can contact me privately via the contact information provided on the class website. I thank you for your kind attention in the introduction to IPv6 on ScreenOS devices, being able to configure host or router mode for your ScreenOS firewall.